Hello, Chem 110. Today we're going to begin our discussion of thermochemistry. After this lesson, you should be able to differentiate between a balanced equation and a thermochemical equation, draw an energy diagram to keep track of the enthalpy change for a given reaction, determine what that enthalpy change means in terms of whether a reaction is endothermic or exothermic, and also determine the enthalpy change for a reaction given a thermochemical equation and the amounts of reactants or products given. You also want to be able to understand how the state of matter can affect the overall enthalpy change in a reaction and be able to determine the fuel values for different compounds. So let's get into it. This slide hopefully will look familiar. It is diagramming some of the different phase changes that we've seen in a way to help us keep track of which phase changes are endothermic and which phase changes are exothermic. So our endothermic phase changes are melting, evaporation, and sublimation. And these are endothermic because we have to add heat to disrupt intermolecular forces holding molecules together. And then freezing, condensation, and deposition are exothermic, and that energy is released as heat as our more condensed phases are formed. Okay, so this is hopefully all review. Okay, and so we can remember that enthalpy is keeping track of the heat that's transferred at a constant pressure. We use delta H to represent our change in enthalpy, and a positive delta H represents an endothermic reaction. So we have to put heat in, heat is entering. With a negative delta H, that means our reaction is exothermic and heat is exiting. And we feel that heat when we put our hand up next to our beaker, because we can feel the temperature of our surroundings increasing as our reaction releases heat. So the reverse reaction of an exothermic reaction will be endothermic. And we'll look at that a little bit more as we continue our conversation. And so go ahead and take a moment to pick out which of these changes you believe are exothermic. Okay, so let's go ahead and look. So ice melting would have to disrupt, it would be going from the solid to the liquid phase, and we would have to disrupt intermolecular forces. So we would have to put in heat. So this would be a positive delta H and be endothermic. The same goes for water boiling. We would be going from the liquid phase to the gas phase. So we'd have to disrupt a whole lot of intermolecular forces. Wood burning, I'm sure you all have experienced this, and when you get close to it, it's hot, right? And that's because this reaction is releasing heat. And we'll say that any combustion is exothermic by definition. And then for water freezing, we're going from the liquid to the solid phase. And so this will be also exothermic, which is why we have to put water in our freezer. To make this reaction happen, we have to suck the heat out of the water. Okay, and then the sublimation of dry ice would be going from solid to gas phase. We'd have to disrupt intermolecular forces, so this would be positive delta H or be endothermic. Okay, so the correct answer in terms of the multiple choice portion would be B here. So when we talk about enthalpy, we oftentimes refer to it as a state function. And that means that it doesn't matter, what steps we take to get from point A to point B. It only matters what our final and our initial states are. So we say it's path independent. And we also say it's an extensive property. What that means is it depends on how much of our stuff we have. And I'm sure you've experienced this in real life. You know, to melt an ice cube at room temperature doesn't take very long. But then those giant mounds of snow that accumulate in parking lots from people plowing, those take forever to melt, right? Because they're large, they require more heat. Okay, so if you were to double the amount of material that you react, you'll double the enthalpy change. And so we can consider the combustion of hydrogen, which is what we oftentimes refer to as the balloon reaction. And of course, I don't have a balloon here, but I do have a video of a balloon, which is almost the next best thing. So let's go ahead and look at this. Okay, so we could see here this big spike in the temperature. In the thermometer, we can see the temperature increase. And so that is showing us that this reaction is exothermic. It's releasing heat. That heat goes into our thermometer, and we see an increase in temperature. Okay. And so one term that we should define for our conversation about thermochemistry is chemical energy. And so that's the potential energy that's associated with bonding. And so when we change bonding, we change the energy contained within our products or our reactants. And so that's where we get this change in enthalpy from. And so that combustion, as we've said a few times now, it's exothermic. Okay, so there we have our reactants, the hydrogen and the oxygen gases, and they form gaseous water. And so what we have here is our balanced reaction, our balanced molecular equation. But for this topic, oftentimes we want our thermochemical equation, and so this gives us some idea about the enthalpy change. And so to do that, we're going to tack on the delta H for the reaction. And so here we can see it's negative 483.6 kilojoules, which makes sense. We said it was exothermic, so it should have a negative value. And that's telling us then that our products are at a lower enthalpy value than our reactants. So that decrease then is our delta H of reaction. And then that heat, of course, is lost to the surroundings, which we've oftentimes felt when in the forum. Okay, so this delta H value, this negative 483.6, is written kind of for one turn of the reaction. And so we said it doesn't matter how much of our material we have. And so if we're considering this delta H from the perspective of water, this value is really written for 2 moles of water being produced. So if we wanted to look at only 1 mole of water, one way we could do that is just divide all of the coefficients in our reaction by 2. And then we would divide our delta H value by 2. And so then we would find that we get a delta H of negative 241.8 kilojoules for this situation when we have 1 mole of H2O produced. And we'll see some more examples of looking at that shortly. Okay, So in the video, and as we've seen in class, we've seen that forward reaction of the balloon, or the combustion of H2 gas, and it is exothermic. So then what if we were to do the opposite, the reverse reaction? What would its delta H be? So we would just be going the other direction. And so we would change the sign on our delta H. So the magnitude stays the same, it's just now our sign changes. It's the directionality of our heat. Whenever you flip a reaction, you flip the sign for the delta H value. Okay. So that brings us to our example of an endothermic reaction. So let's go ahead and look at a video in the ebook for this reaction. This is actually one of my favorite demos. I'm a bit disappointed we can't do it in person, but let's take a peek. So let's go ahead and watch a video of an endothermic reaction.
Water is poured on a wooden block, and a beaker equipped with a thermometer probe is placed on top. Solid barium hydroxide octahydrate is added to the beaker, followed by solid ammonium thiocyanate. An endothermic reaction begins immediately, and even before the solids are mixed, we see the temperature within the beaker begin to drop. The reactants are stirred to facilitate contact between the solids, and the temperature drops rapidly to 0 and then below. The reaction is driven by favorable entropy, as solid reactants are converted into products in solution. As the reaction is endothermic, the heat required for the reaction to proceed is withdrawn from the surroundings. Accordingly, the temperature of the contents of the beaker, as well as the water below, drops. The temperature drop is so drastic that the beaker becomes frozen to the wooden block.
Okay, so there was our endothermic reaction, and here we have the equation for it. And what we see is, as a result of this reaction being endothermic, we have to add heat in, and the enthalpy of our products will be greater than the enthalpy of our reactants. And as such, the temperature drops of the surroundings because we have to input energy to make, in terms of heat, to make this reaction. And so what happens is that the absorbed heat is converted into chemical potential energy stored within the bonds of our new products. Okay. And so if you're ever unsure what we refer to by surroundings, generally the thermometer is measuring the surroundings, just to keep that in mind. Okay, so we mentioned before that the phases of our different molecules changes the enthalpy of our reactions. And this makes sense because different phases are experiencing different amounts of intermolecular forces, and so that will change the amount of stored energy. And so what we have here is the combustion of methane as our first reaction. So you can see we have methane, we add an oxygen, get out CO2 and water. And combustion is always exothermic. And so when we start with our methane and add oxygen to it, we'll lower the energy of our products. And the value associated with the combustion of CH4 is negative about 800 kilojoules. And so as written in this first equation, we have gaseous water given off. So the next we can think, well, what if we instead were to have liquid water? We would have to have some condensation reaction as we go from the gaseous phase to the liquid phase, and condensation is exothermic. So we would see again another drop in the enthalpy. And the delta H value associated with this is negative 88 kilojoules. So then if we are going to combine these two reactions, we can kind of cancel out our gaseous water and replace it with the liquid water. When we add those two equations together, we will just go ahead and add their enthalpies together, giving us a delta H value for this reaction of negative 890 kilojoules. So when you're working through these problems, you do want to be really careful that you're paying attention to whether you have something that's liquid or something that's gas. And as we start doing more problem solvings, use the appropriate values for those. Okay, just reiterating, add two equations, add the delta H's. And so here we can see a combustion reaction that we do all the time. We have the combustion of sucrose. And so we're going to try to figure out how much energy is released when 50 grams of sucrose are combusted. So what I want you all to do is pause and try to work through this problem on your own. Okay, so 3, 2, 1, pause. Congratulations on working through that problem. Let's go ahead and review it. So we're starting with 50 grams of sucrose. And you know, we never really want to work with grams. We want to get our values into our currency of moles. We can do that using the given molecular weight. And so we'll have 0.146 moles of C12H22O11. And so what we can do is we can take that amount of moles and multiply it by our delta H value from above, divided by the coefficient for the molecule of interest in our reaction. So in this case, it's just 1. And then we can calculate our amount of heat that's released when we combust 50 grams of sucrose. Okay. So if you were able to work through that, great, congratulations. And so, you know, this topic of sucrose reminds me of food. Okay, because sucrose is a type of sugar. We know that our bodies harvest energy from our food. And sort of the most common idea of kind of food is sugar. And so here we have the formula for glucose. And then the balanced equation and then the thermochemical portion for that reaction. And so if we're working on interpreting what this thermochemical equation is telling us, you can see that for every 1 mole of sugar that's combusted, we're going to get out just 2,803 kilojoules. But then we can say, well, what if we are producing 1 mole of CO2, how much energy would be produced? And so then what we're going to have to do is take our delta H value and divide it by the coefficient on CO2, which is going to be 6. So this delta H value is telling us for every kind of 1 turn of the reaction. And for every 1 turn of our reaction, we have to put in 6 moles of CO2. So we would have to divide by that value and see that for every 1 mole of CO2 that's produced, we would get out 467 kilojoules. So here we were working in terms of moles, but when we're, looking at nutritional information, we're never looking at moles of sugar in a can of pop or anything like that. What we're looking at are grams. And so we could calculate how much energy we get out for 1 gram of sugar. And so we can take our delta H of reaction. And so this delta H value is telling us that we have negative 2,803 kilojoules for every 1 mole of sugar. And then we can just use the molecular weight of sugar to convert. So for every 1 mole of C6H12O6, I have to put in 180 grams. My moles will cancel. And then I can see that the delta H of the reaction for 1 gram would be negative 15.6 kilojoules. So for every gram of sugar that's consumed, we would get out 15.6 kilojoules, which is about 3.7 calories. And so nutritionists are oftentimes looking at the fuel values for different categories of food. So this value here that we calculated, where we have the energy given off per gram, this is what we would denote as the fuel value. And so here they kind of generalize what a carbohydrate means, and they say the fuel value is about 17 kilojoules per gram, which is pretty close to what we calculated for sugar. And then they can figure out, how much energy we get in terms of calories for every gram of CO2 that's produced by consuming these different types of food. And then I don't know about you all, but one of my favorite foods are apples. Okay, so food is one type of fuel. It's, what we use to fuel our little combustion engines that are our bodies. But there are other types of fuels too, and we can also determine their fuel values. So here we have the reaction for the combustion of octane. So this is like what our cars do. This gas roughly is the same as gasoline. And so we can see when we have 1 mole of octane reacting, we get out about 5,000 kilojoules of heat. And then here we have methane, which is natural gas. And its combustion of 1 mole of methane would generate about 800 kilojoules of heat energy. And then here again, we have sugar, which, as we saw before, gives off about close to 3,000 kilojoules of energy for 1 mole. And so we can continue to figure out the fuel values for different hydrocarbons or different fuels by taking the delta H value for 1 mole of that compound and dividing by the molecular weight to get how many kilojoules would give off for 1 gram of that fuel. And so here we can see these fuel values for octane, methane, and hydrogen. And so we can see octane and methane are fairly similar when you compare their fuel values in terms of grams. Then here we can see hydrogen is way more efficient. It gives off a lot more heat. And it doesn't produce any CO2 in its combustion. The hard part is, it's really small, doesn't have many intermolecular forces, and so it exists as a gas. And it's pretty hard to condense that down into a useful form. And then also we can figure out how much energy we get out per gram of CO2 that would be produced, similar to what we did on the previous slide. And we can see that methane, or natural gas, does give us a bit more energy per gram of CO2 that's produced than octane. And so we could consider methane to be slightly cleaner than the octane. We have a similar challenge with methane though. As I mentioned, it's natural gas. It also tends to exist in the gaseous form. Though it does have more intermolecular forces than H2, it's bigger, more London dispersion forces to hold it in a liquid phase. Okay. And so with that note, I kind of want to end with a sort of charge for you all to try to help us develop fuels that are greener, that produce less CO2. And so we want to increase that fuel value and increase the kilojoules given off per gram of CO2 produced. And we can see that right now, only about 10% of our energy sources come from, or of our energy comes from renewable sources. And a decent amount comes from natural gas, which is that methane we looked at, which was slightly cleaner than octane or coal. But then, so hopefully this pie graph will one day look like this, where just 100% of it is renewable. Okay. And with that, I'll let you all go. I hope that you have a great day, and I'm gonna go eat this apple. Talk to you soon.